let's just say that the coordinates of a point, so x and y, right, are dependent on a third variable, t. Okay, for example, let's say I asked you, let's just pretend you've never studied parametrics in your whole life, and I just gave you this following problem. Let's just say I say, all right guys, I want you to graph root t, t minus 2. Root t, t minus 2. You'd be like, what are you talking about? What's t? Well, what if I told you that t was a number between 0 and 4? Inclusive. Now you might think, oh, okay, I get it. You want me to plot grad t as my x, and you want me to plot t minus 2 as my y. Right? So you're kind of telling me what t's to try plugging in here. That's exactly right. I'm saying, look, let's plug in 0 and 1 and 2 and 3 and 4 from here into there. We'll get some x's, we'll get some y's, and we'll form a plot. Okay, so you might look around and say, well, where's the graph? And Mr. Shore has this drawn for you. You're supposed to fill this in, see? And this says x and this says y. How are you going to do this problem? Well, you have enough problem solving skills to know that you should at least try plugging it in. So why don't we make a quick table? We'll write the t value over here. It looks like we're just using 0 through 4. So let's write 0, 1, 2, 3, 4. And then we'll use the second column to calculate what our x is, and the third to calculate what y is. The fourth column will just be there to know what we're going to plot. So, what's rad 0? 0. What's rad 1? 1. What's square root of 2? Yeah, it's rad 2. It's about 1.4. If you're plotting, it might be nice to know the decimal. Next would be rad 3, you see. It's pretty close to 1.7. Rad 4, obviously, is just 2. So we just filled out the first column by doing rad t, rad 0, rad 1, etc. That's right, pretty rad. Okay. Now it's time for the y column. How do we find our y's? Well, it would be 0 minus 2, 1 minus 2, 2 minus 2, 3 minus 2, 4 minus 2. In other words, the answers are negative 2, negative 1, 0, 1, 2. But you're trying to plot on an xy grid, so it sounds like we're going to need to take this as our first point, 0, negative 2, and then 1, negative 1, 1.40, 1.71, 2, 2. So those seem to be the points we're plotting, you see. So let's just see what it all looks like. We shall be plotting 0, negative 2, which is down here, of course. 1, negative 1, which is right here. 1.40, which is right about there. 1.71, which is right about there. And 2, 2, which is right there. Anyone care to guess what shape that is?
Parabola.
Parabola. I like that. He said it's a path of a parabola. You're right. It's actually... You said a half. It would have been perfect if you said path. But what's going on here is this is like a moving... It's half of a parabola. It's like a moving object, and it's following the path of a parabola. See? So, what we need to do is, we need to say, first of all, this is not a parabola. Okay? A parabola is a static curve. It has no start, no stop, and no direction. This is a moving object, moving in a parabolic fashion. Okay? So there's a difference. What you need to do now is connect the dots, because there's plenty of in-betweens that we never plotted. You also need to identify the starting point and the stopping point of this motion. And then you need to also add these little arrowheads to indicate the direction of travel. But this is not a parabola. It's like Arn said, it's half a parabola. It's not even that. It's not even half a parabola. It's a portion of the right half of a parabola, right? You probably would even guess that the vertex of this parabola is right there at the starting point. But how to be sure is a different matter. How do we know that this is actually the path way that the graph is following? Is this really, y equals x squared minus 2? Is it that simple? Maybe. Now we're going to test it. Okay, so to determine the green path, which is not the same as the red path, okay, we're going to try to eliminate our variable. So to determine the path the point is traveling along, we need to eliminate the parameter. We need to eliminate t from the problem. So remember, x was just root t, and y was t minus 2. If you take this first expression and you square both sides, you actually get x squared equals t. Okay? And if you take that and you plug it in right here, you can see that y is equal to x squared minus 2. Just as we suspected, it really is a parabolic path. So it's okay to say, I think that's a parabolic path. It's not okay to say it is a parabolic path. You have to kind of show that it's a parabolic path. It wasn't hard to do. I just isolated t in one equation and plugged it into the other. Sure enough, it's a parabola, and it's exactly the one I thought it would be. Let's try another one. Okay, so example 2, graph x equals 3 cos t, y equals 2 sine t. Then determine what shape it is, what path it is on. So we'll do the exact same thing as last time.
From where to where?
Okay, so the t will range between 0 and 4 pi. So when we make our table, we're going to use 0, probably pi over 2, maybe pi, 3 pi over 2. Be nice to yourself, right? This is your now kind of like your independent variable. Don't pick like crazy angles you can't handle, right? If you need more details later, you can always add more points. Let's just go to 2 pi for now, and then we'll talk about what happens when you go all the way to 4 pi. Okay, so I like to do the x column first. I did that on last problem too. To get to x's, you're supposed to do cosine t and then triple it. So what is 3 cos 0? It's just 3. What's 3 cos pi over 2? It's just 0. What's 3 cos pi? It's negative 3. What's 3 cos 3 pi over 2? It's 0. What's 3 cos 2 pi? It's 3. And I kind of stopped at 2 pi. I'm supposed to go all the way to 4 pi. But you know what? It's just going to recycle. 2 pi represents 360 degrees, or one full cycle. So you can go on if you want to. The next would be 5 pi over 2, followed by 6 pi over 2, and so on. You might as well just not, because you're just going to get these same values all over again.
What just happened? What's just...
Oh. Sorry about that.
I wasn't looking. I heard I was...
That was kind of scary for everyone, right?
that hard.
Okay, let's look at the
What just happened?
y equals, oops, that's not a pen, that's a highlighter. I don't tend to write with highlighters. Y is supposed to be 2 sine t. 2 sine t. Okay, so let's go ahead and try this now. It's going to be 2 sine 0, which is 0. 2 sine pi over 2, which is 2. 2 sine pi, which is 0. 2 sine 3 pi over 2, which is negative 2. And 2 sine 2 pi, which is 2. No, it's 0, sorry. Okay, time to plot. Remember, I only did half the table I was told to. Okay, the first point is at 3, 0. We saw last time. You just take these as your coordinates. So 3, 0, 0, 2, negative 3, 0, 0, negative 2, 3, 0. So let's plot those guys. 3, 0, I'm going to write start there. Start. Next point is 0, 2. Next point is negative 3, 0. Next point is 0, negative 2. And interesting, the last point in this table that I've created goes back to the first point. So it looks like I kind of just went all the way around like this, and I'm back to home plate. But I'm not done yet because I'm supposed to go all the way to 4 pi. So what's going to happen is it's going to go around again. So it goes around one time like this, keeps going, around, 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 and it actually stops right where it originally started. So it forms a closed, what? What is this thing?
I know, ellipse. Sorry.
An ellipse? Most likely it's an ellipse, right? So how do we test? How do we know for sure? It probably is an ellipse.
You substitute stuff.
Well, what we did last time to test for what kind of path it was we tried to eliminate t from the problem. So let's try to do that. So I'll write this again. To determine the path of travel, to determine the shape or path, eliminate t. Now last time I had, just rad t and t minus 2. They were pretty simple to work with. This time it's a little more complicated. I've got 3 cos t and 2 sine t. If I try to isolate t in one of these, it's going to look awkward.
The arc cosine of x over t?
Yeah, and then I have to plug that into the other equation. That doesn't sound very exciting at all. So what I'm going to do is remember a good old rule called Mama's theorem that says cosine squared t plus sine squared t is 1. Cosine t squared plus sine t squared is always 1. This is just an identity. It's always true. So what I'm going to do is isolate cosine t and sine t in this problem. So a slightly different approach from last time. I don't know what I'm doing. I tried to move something, and instead it just kind of jumped. That was weird. Okay, so we're going to isolate cosine t in the first equation. Why don't you guys go and do that? Cosine t is x over 3. And we'll isolate sine t in the other equation. Sine t is y over 2. And we'll substitute those guys into these spots, like that. So it reads like this. X squared over 9 plus y squared over 4 equals 1. Sure enough, as Hunter suggested, it's ellipse. And we know which equation it is, too. Okay, so is the red thing an ellipse? Technically, it's not an ellipse. It's called... Okay, the path is an elliptical path. The object is moving twice around an ellipse. Maybe it's a planet going around the sun, right? 2 years. Well, 2 times for the Earth around the sun is probably a year. 2 years, right? So anyway, this is the path. This is the plane curve. It's called PLANE curve. Let's label it real quick, because that's kind of a new vocab term. This is called a plane curve. So a couple of ways it's different from an ellipse. One is it's a moving object. Two, it has a start and stop and a preferred direction. The ellipse is just a static, brainless curve, right?